Yeah, greetings, everybody. Welcome to this edition of the Alliance for PE Pipes webinar series, where today we're lucky enough to talk HDPE versus PVC. And what an opportune time to do it given the market conditions. As always, let's spend a few minutes getting acquainted with the Alliance because we have several hundred people on the call today, and many of them are new, although we recognize some of you have seen this before. But we are a trade organization. We believe we have a better solution. We've got a lot of companies behind us, and these are those companies that have a story to tell. Certainly there's a commercial interest today, but we do our best to tell an honest and forthright story. We thank our members for supporting this and the other programs that we offer. You can join the Alliance even if you're an engineering firm. We'd love to have you. It gives you first dibs to whenever we're in town, and many of our offerings that are free. And many of you have followed us on social media. We're very thankful for that. We've got close to 17,000 followers now. LinkedIn is our most active format for that. And we have an active slate of programs coming up. We're going to be in Alaska next week. Then we're going to be in Charlotte with the APWA. That's a great show. If you've never attended that event, we're really the only pipe type that shows up at that event. We're going to break some pipe. We're going to break some PVC as well as some cast iron pipe in our booth at that show. Our next webinar will be with ASCE on September 19th. And then the day after that, Alan Ambler will be back to talk about pipe bursting. That's our webinar series. Only engineers can join the ASCE on the 19th of September, but anyone can join us on the 20th to learn about pipe bursting with HDPE pipe. And as always, we have a lot of free resources. Our engineers are very busy with seminars and private one-on-one sessions with engineers and owners talking through their projects. These webinars are great resources for us because it channels a lot of your interest in the product by asking us to help you with your projects. So please keep taking advantage of that. Alan Ambler, you've decided to undertake a new engineers package for next year. Tell us a little bit about what's in store.
Great. So we are revising and adding material to the engineers package that was released in May of 2020. We have learned a lot from you about what you want to see in the engineers package and how it assists you. You've shared specifications with us. You've shared project details and plans, and that library that we have just continues to grow and grow and grow. So for this one, we've added a specification on slip lining, compressive fit slip lining, and some others, some additional typical details. And then we're also really pushing up quite a bit on testing. So we're getting our hands dirty and deep into testing. And then we'll also, of course, in normal fashion, make it very light and normal layman's terms for you too, if you're not interested in that heavy and deep. So here we are. We're going to anticipate rolling it out at the end of this year, Pete, if we have any luck. And thank you very much for asking.
Yeah, thank you, Alan Ambler. All right, Stephen Boros, why don't you come on? As always, whenever we have more than 200 people attending, we always bring on a deep bench. And heading that bench today is Stephen Boros. Welcome, Stephen.
Thanks, Peter. Hi, glad to be here today. Looking forward to all the questions and answers and everything we have to offer. So thanks a lot. Thanks for having me.
Yeah, so Stephen will head that bench along with two other engineers. We have Matt Hahn. Matt, welcome.
Hi, Peter. Good to be here. At Performance Pipe, we're a division of Chevron Phillips Chemical, one of the resin suppliers. So we've got the benefit of that experience to provide to our customers. Looking forward to help out here.
Yeah, well, thank you for that, Matt. And then we also have Richard Kalasa. I found a good picture of Richard because Richard said, Peter, I'm not coming on today because Richard has COVID. He's not feeling too well. So just know that Richard will be there as well. And then, of course, our headliner is Dusty Langston. Dusty, why don't you come on the screen? Welcome. Tell us a little bit, Dusty, about who you are and what you do.
Thanks, everyone. I also work for WL Plastics, co-worker with Richard Kalasa, even though his picture is way better than my picture. Just throwing that out there. But I'm VP of Engineering and Quality Assurance for WL Plastics. Been with WL Plastics for about 17 years now. No, 18 years. And engineering degree from Southern Utah University and a member of the PE Alliance. Absolutely love doing these presentations.
Yeah, so several years ago, Dusty decided to become the industry's expert on the comparison between these two products. We have an annual show, and Dusty prepared the initial deck for that show and did a great job, along with Harvey Svetlik, in developing it. And we keep working on it, keep getting it better. And I just have a few words now that we have over 300 some people on this call. I wanted to say thank you to everyone for coming on today and participating with the Alliance in our webinar series. You know, we've developed a reputation of delivering high quality, honest content without the sensationalism that you get in other venues and perhaps a little overreach. The team that's on the call today and the questions, and Dusty and Alan particularly, we've worked hard to tone down a little bit of the rhetoric and really make a very honest portrayal of our view. The turnout for today, I think, is proof that the integrity of our content, our reputation of doing this over time is resonating in the waterworks profession, certainly with engineers and municipal owners. So we thank you for that. Speaking of Harvey Svetlik, he's a frequent talker and been a leader in the industry over the years. I'm reminded of comments that he made at Showcase several years ago, guys, where he said he's comparing the three pipe types, ductile, PVC, and polyethylene. And he said, you know, ductile iron was a good pipe for its time. It solved the issues with thin wall cast iron, those circular failures, and it traded one failure mechanism with another, so that being circular fractures, which is characteristic of thin for tuberculation. And circular failures tended to be catastrophic, whereas the tubercules and those small holes that show up in the ductile iron tend to not be catastrophic. Just put a band clamp on it, and you'll get another 3-4 years out of that pipe segment. And then Harvey went on to say that PVC is a good pipe. It was inexpensive. It was lighter than ductile. It went together the same way, and guess what? It was plentiful. We got a couple new failure mechanisms with PVC, though. We now have a brittle pipe. We have separation at the bell and the spigot. And Harvey talked about it being kind of like a pitcher's arm. You know, a pitcher's only got so many throws in that arm. Same thing with PVC. With cyclic fatigue, it only has so many cycles before it suffers from fatigue. And you have to be careful putting it together, as Dusty will talk about, with mechanical equipment and the hydraulic equipment, sticking it together. Harvey finished by talking about polyethylene. Polyethylene's a great pipe. And the reason it's great is because it has solved for the typical failure mechanisms of the other two dominant pipes. Namely, it solves for tuberculation, just like PVC does. It solves for overinsertion. You don't have an overinsertion problem. It solves for fatigue. It solves for leakage. And importantly, it solves for ground movement. Just look at Houston this past week with 500 failures over the weekend. Imagine that, 500 failures in one day. And in Houston's case, the biggest user of polyethylene in the United States is Houston on the wastewater side. But on the water side, they refuse to use it. They continue to use bell and spigot pipes, and they continue to have massive failures whenever drought times come by. So in that context, I think Harvey did a great job of setting the stage for today's call. And finally, we have a few people that represent other pipe types. I encourage you all, as well as the engineers that love using other materials, that may think that we're wrong, let us know, because correct us. We want to know if we're wrong or if we've overreached, because that's how we get better, and that's how we maintain your trust. So with that, I encourage you to answer that poll question. We can get started. And Dusty, I am going to turn it over to you, my friend.
Awesome. Thanks very much, Peter. Yeah, as a reminder, everybody take that poll that is up on your screen. Please ask questions as we go along. I'm going to go ahead and share my screen now.
Great. I think I just stopped sharing, so you're good to go. Thank you all for listening, and we'll see you when questions come up.
Perfect. And I just want to confirm real quick that it is indeed showing, correct?
It is.
Beautiful. All right. So thanks, everybody. Excited that we have the turnout that we have today. Great turnout. Over 600 people signed up today for this webinar, and we're going to talk about PVC and polyethylene pipe. And of course, right when I share my screen, it goes crazy.
Before we do that, we're going to give you some of the results of the poll here, Dusty. I know everybody's patiently waiting, so we're going to get that drum roll, please. So 14%, it said difficulty getting PVC has caused us to consider HDPE. My second favorite, just because it's totally honest, 28% said my boss told me to educate myself in HDPE. And at one point in time, my boss told me to educate myself in HDPE as well. So you're in good company. 18% said the infrastructure bill is supercharged funding for infrastructure projects, water projects, and that is good to hear. My biggest thing is let's go out and get work done. We know that there's a whole lot of it out there. Let's get it done. And 40% of you, this is a nice one. I have an active project I'm considering for HDPE. And again, part of the nonprofit Alliance for PE Pipe Service is to help you in pursuit of whatever project it is that you're considering and doing. And we would be more than happy to help you. So with that, Dusty, take it away. Plus, don't forget questions, guys. You can type your questions in. We got a full team answering them for you.
Beautiful. Thank you very much, Alan. So what are we doing here today? Ultimately what we're trying to do is, oh my goodness, this is horribly embarrassing. For some reason, it started me out on the very last slide, so I apologize, everyone. So what we're here today to do is really to get you to take that second look at polyethylene pipe. As the poll just showed, a lot of people are here because there are shortages of other pipe materials. Had a call just yesterday. Hey, looking for some polyethylene pipe, looking for some 16-inch. We cannot find 16-inch ductile iron in Texas right now. So we really need some help on, understanding flow comparisons and everything like that. And that's exactly what our job is we're here to educate people on different pipe materials and HDPE pipe and the comparison between those and other materials. And that's the whole reason you guys are here today. So I thank you very much for everyone being on this webinar, and let's really get into it. So Peter talked about this a little bit, the natural evolution of, metallic and even before metallic, wood stave and clay pipes to, the plastic generation, PVC and polyethylene. And, for their time, cast iron pipes were fantastic. Even wood stave, there's a lot of people don't know this. There's still a lot of wood stave pipe in the ground today. A lot of people don't know that. Cast iron is the exact same thing. And that's what the ductile iron industry talks about with their 100-year, centennial club is, they're talking about cast iron pipes that have been in the ground for a very long time. And they're very thick walled. But like Peter talked about, there were some problems and ductile iron fixed some of those, as did PVC fix some problems that ductile iron had. And at polyethylene, we feel we have the solution for today. So a little bit more of that history. We go to these trade shows all over the country, give presentations all over the country. And it always makes me sad to hear when people say, oh, well, you're that new pipe that I've been hearing about. I'm just like, oh, stab in the heart. Not new. We've been around for a long, long time. PVC was commercialized in 1965 with an AWA standard. Polyethylene HDPE pipe was commercialized in 1967, so just 2 years later. And then ductile iron was only, so formal ductile iron had their first AWA standard in 1963. So we've all had an AWA standard about the same amount of time. And where polyethylene pipe was a fusible product when it was first commercialized, we decided to chase after other welded products, which is steel pipe. And so we started going after anything steel was used in: natural gas, oil and gas gathering, really mostly the energy markets. PVC pipe came out about the same time. It solved for a lot of the issues of metallic pipes and water systems, and they were a bell and spigot jointed pipe. And so they chased the water market. And in those times, we have become almost the predominant player in both of those markets. So PVC by far makes up the majority of water and sewer pipes going in the ground today, as polyethylene makes up the great majority of lower pressure, lower than 300, 400 PSI, where steel used to be. In oil and gas gathering and in gas distribution. So over the last 50 years, both polyethylene pipe and PVC have been very busy, and we've become the predominant players in those markets. HDPE pipe in the last really 10, 15 years has decided, we really do have a fix for a lot of issues that the water and sewer industry markets see, and we need to be offering our product in those markets. So that's why you have considered us the new kid on the block up until now. So a little bit more on the history. Peter touched on this a little bit. Cast iron pipes, again, very good, a very thick walled product, but they were susceptible to overloading, causing circumferential cracks, fracturing. And these were catastrophic. They would, be big breaks. And that was just usually from overloading. If you overloaded that pipe type, put a building on it, under a road, things like that, overloaded, that would fail with a circular fracture. Ductile iron came out and said, nope, we can fix this. We're going to come in, we're going to change the chemistry of this metal, and we're going to make it so we get away from these circular fractures. And it absolutely worked. They got rid of that completely. But our new susceptible failure type now is corrosion. And so asbestos cement pipe, during World War II, we really didn't have a lot of metals to use. So we had to get creative. So asbestos cement pipe came out, and it's now at the end of its life, and it's failing in that same style, which is mostly circular fractures and then joint failures now. PVC, this is a completely different type of failures that we're starting to see with PVC pipe that's never been seen really in the water market before. And we'll talk a little bit more about this at the end of the presentation. But, we don't really have the circular fractures. Obviously, there's no corrosion. Same with polyethylene, no corrosion. But axial fractures have become the new failure type that we really need to talk about. And a lot of these failures are from poor installation. Flat out, PVC can have a very long service life if it's designed and especially installed correctly. The city of Calgary actually did a study here. This is about 5-6 years ago on their PVC system and their ductile iron system to see why it was breaking, what the costs were associated with those breaks, and how long service lives usually were on these products. And so city of Calgary, for those that don't know, in Alberta and Canada, over 1 million services in that city. And the findings of their report was ductile iron was by far failing more than anything else. Pinhole leaks, tuberculation, corrosion, average 15.9 breaks, so 16 breaks per 100 miles. PVC was breaking much less frequently, about 1.2 breaks per 100 miles. They also did have polyethylene in this. We don't like to show the data just because they didn't have a lot of polyethylene, but of course the break rate was much less with polyethylene. But again, that kind of skews things because we really didn't have a lot of miles in the city of Calgary. But so PVC had much less, much fewer failures than the ductile iron systems. But in that time, they started to realize that, hey, even though we're having 7.5% the break rate of PVC, PVC, when it did fail, it was failing catastrophically in these axial long running cracks that would destroy whatever infrastructure was above it. And so even though it was 7.5% the break rate, it was 764% the break cost. So to excavate down to a ductile iron pipe and put a band clamp over a corroded area, very inexpensive, did very little damage above it. When a PVC pipeline came open, unzipped, if you will, it created a big pothole, a lot of damage. It was very expensive.
Hey, Dustin, we had a question live. Do you just want to address fusible PVC, and have you had any issues with joint failures with fusible PVC versus bell and spigot?
We'll talk a little bit about fusible PVC later in the presentation, and we'll touch on fusion as well. Fusible PVC is really, really new out there. We do have some data, especially some testing that we've done that does show the tensile strength of the fusion isn't exactly the pipe tensile strength, where polyethylene pipe, the strength, the joint strength is as strong as the pipe itself. But we'll go over that here a little bit more in the end of this presentation. And thank you, Richard, for that. So moving on, ultraviolet radiation. So a lot of plastics are susceptible to UV ultraviolet degradation. If you ever leave a clear soda bottle out in the sun, you'll see it kind of browns and yellows and kind of starts to degrade. With polyethylene pipe, we use a carbon black additive in this pipe so that you can actually store it above ground. You can install it indefinitely above ground. It is completely UV stable for the service life of that pipe. Everybody's seen a pipe yard like this. This is actually in my hometown where I live here in Utah. This is a small town city of Enoch. And I don't know why they actually keep this pipe. I would hope they recycle it at some point because at this point, none of it's usable. Everybody's seen a pile of PVC or other plastic for that matter, that if you leave it out in the sun too long, it actually starts to break down. It's called dehydrochlorination.
So Dusty, with polyethylene though, the gray pipe, which is polyethylene, it's just like PVC, you can't leave it out in the sun, right?
No, that's a good point. So you can get polyethylene in different colors, blue and gray, for example. We are still UV stable up to 2 or 3 years. I've asked the PVC guy several times, like, what is your recommendation? And they really don't recommend any outdoor storage. You know, if it's going to be outdoors, please cover the bundles of pipe. So polyethylene, if you get it for gray for sewer pipe or blue for potable water, these are just options. Most of the time it comes in black with whatever color stripe you want. It's a 2 to 3 year UV resistance for those colored polyethylene pipes.
Okay, so that's the gray, but standard black is indefinite outdoors. Is that correct?
Yeah, we have lots of applications where it's been installed 50 plus years above ground in mines, all kinds of applications.
Thank you.
As we spoke more in the last webinar, one of the reasons to do a white interior or gray pipe is it reflects the camera, the CCTV camera light better in gravity sewer inspection. So the industry had seen that as a need and subsequently invented Camcore and other products to be able to do so. So that's there you have it.
Yeah, that's correct. If you were to send a camera inspection down a black sewer pipe and turn the camera on with a flashlight, it kind of washes out. You can't see very far in front of you. So we started using these gray pipes or gray interior liners to make sure that you can have good camera inspection in your sewer polyethylene pipe systems. So back to dehydrochlorination, this process, once it begins from UV damage, it actually keeps going in PVC, and it actually can decrease impact strength or impact resistance. And so with PVC, you know, well, why doesn't PVC just put black in their pipe, you know, like polyethylene does? And it, you know, they might be able to get away with that if they weren't storing it outside. But with PVC, if you were to put black in it, the pipe temperature gets very high. And HDPE pipe can handle those higher pipe temperatures from that high UV radiation. But for PVC pipe, it just can't handle the high temperatures that come with being a black pipe. So bend radius, HDPE pipe is by far the most flexible water pipe type out there. Anybody who's used polyethylene pipe for service tubing, for example, knows this. It's absolutely one of the biggest benefits of using polyethylene pipe. One of our claims to fame is you can take an 8-inch dips polyethylene pipe, wrap it around a standard 40-foot cul-de-sac with 0 fittings. It's flexible enough to do that, and you can still make all your service connections off of that bend arc. PVC, for example, it's 250 times the diameter for polyethylene pipe, and it's 25 times. And all the deflection takes place inside of that bell and spigot joint. It is not allowing you to bend the the barrel of the pipe. Same goes for cast and ductile iron. They have the exact same bend radius because the bend, again, is taking place within that bell and spigot joint. Alan, do you have
we saw some history that Dusty brought to us a little early in the slide, but the way that we're installing pipelines now has come a fairly dramatic distance from 1960s when these 3-pipe material types were installed. So the bending radius, the allowable bending radius, the durability and forgiveness that this pipe material really provides is what shines in trenchless applications. So this slide here, even though it just the numbers and shows you the bending radius and how forgiving it is, the trenchless itself, it's grown massively because of this phenomena.
Yeah, and towards the end of the presentation, I have quite a few slides demonstrating the flexibility, the ductility of HDPE pipe and why it's so great for trenchless applications. So back to that bell and spigot joint, deflection takes place again inside of that bell and spigot joint for PVC ductile iron. PVC allows 3 degrees of deflection in smaller diameters, only 1 degree of deflection in larger diameter PVC. But failure can occur at as little as 5 degrees. So it's a pretty tight window of what's allowable versus what can cause an actual bell failure in the future. Again, these are installation issues, but this is what the city of Calgary was seeing. So during PVC installation, care is utmost importance. It's especially important to restrain those joints, usually by burying the pipe as you go. If you don't do this, you can actually get a forward over insertion of where you had already been. You already stabbed it to the correct depth, and now we're going to go down line and stab the next joint. If it's not restrained ahead of time, you're going to over insert down line, and that's what this actually looks like right here. Ford Meter Box has invented a fitting to bolt around the pipe to actually prevent and make sure that you do not over insert PVC. But if you're not, again, burying it or restraining it some way as you go, it can be susceptible to over insertion down the line. Somebody, you're trying to stab that new stick in, and all of a sudden things get hung up, you're too much of an angle, whatever the case, and it might have an easier way down line to move that pipe. So very, very important to make sure no over insertion. So Flint actually had some issues like this with a 2-mile, 16-inch line, 14 failures due to over insertion. Peter, are you coming on to talk a little bit more about Flint for me?
Yeah, it was kind of funny, going back to that previous slide, Dustin, we were there in Flint because they asked us to come teach them about polyethylene. I tried for years to get in there, and they have a ductile iron plant in town, and they wanted to use ductile and bell and spigot systems. And then while we were doing this presentation, over against the wall was this piece of 16-inch cracked PVC, Dusty. And I'm like, wow. So I heard the story, and that's how it got there. But, it's easy. Everybody knows about the issues that Flint had. But, I think if you look at Flint and all the issues that you're having, if you could go to the next slide, they're a microcosm for the balance of the United States. Whether it's, wood coming out of the ground, there's still wood in operation, although not a lot of it. They pulled some of that out in the last couple of years. Sinkholes in the downtown. Sinkhole used to be a limestone cavity in rock formations. Now it's cars and vehicles falling in an infrastructure failure caused by high pressure water. Cast iron and ductile iron failures, people taking pictures with huge water main failures, Dusty. What's going on in Flint is going on everywhere. Maybe not all of it at the same time, but when you have a utility that's essentially bankrupt, a lot of bad things happen simultaneously. Flint is on their way out. I'm excited to be part of this process of education and how polyethylene can help solve the problems, but everybody needs to look at this, particularly places like Houston and the big cities that are having huge water loss numbers and large water main break on an annual basis. So Dusty, I turn it back to you. I'm really, I make it kind of sounds like we're picking on Flint. We're not really, because it is a microcosm.
No, you're absolutely right. Flint is the perfect example of so many cities and municipalities across the country, especially in the Eastern US. Flint is just an example of a ton of towns out there that are having these exact same water issues.
Yeah, and I'm kind of excited about the infrastructure bill. I used to think it really wasn't very much, but when you add it, the administration and Congress realized that there is a problem out there. ASCE has been talking about it for years. Finally, it's 55 billion over 5 years, so that's 11 billion a year that our industry gets. Now we're gonna spread it among 3 pipe types, but the engineers on this call, they're gonna have money to fix wastewater treatment plants, water treatment plants, certainly conveyance. So it's an exciting time in our industry.
Awesome. Thank you, Peter. Oops. So moving on now, impact resistance. So again, this is compounded with UV degradation. Hopefully you're getting your pipe in the ground without it being stored above ground, for 6 months, a year, and you don't really have the UV degradation. But PVC versus HDPE pipe is incredibly impact resistant. And let's actually go over that real quick. Have a little video here. This is a video we put together at McElroy Manufacturing. And there we go. Woo! This is what we call the bucket drop test, where we filled a bucket, excavator bucket full of cement. We cut 3 different pipe materials, 4-inch diameter each, 7 inches long, and the bucket weighed 170 pounds. First up, we have cast iron. Anybody who's worked with cast iron in sewer is very familiar with how brittle it is. Here we had, that was a DR14 PVC. And here we have polyethylene. So HDPE pipe, that is also with a fusion in the very middle of the pipe. You can see the difference there. The bucket actually struck it twice because it's so flexible, it bounced. So the bucket actually hit it twice. And again, that was with a fusion in between. I would love to update this year and throw some ductile iron in there. While the ductile iron would not shatter like cast iron, the internal cement liner would absolutely crack and slough off, and you'd have a permanent deformation from that ductile iron hit. So that's a great slide to show, again, the impact resistance of polyethylene pipe. And now it's just going to play this video forever. One other great benefit of HDPE pipe is temperature extremes. So we can, HDPE pipe, even at very cold temperatures, down to negative 130 degrees Fahrenheit, still acts as a ductile pipe material. Where PVC, even all the way up to 220 degrees, it acts as a brittle material. It's still in its gaseous state. And so again, the polyethylene pipe, it can also be used at much higher temperatures than PVC. So it's a better all-around material for those temperature extremes that you might find outside of the water market. Water and sewer, you're pretty consistent with temperatures, but anything, high and low, polyethylene pipe is going to be a great fit. So one of the big things our competition does love to throw us under the bus for is hydrocarbon permeation. Hydrocarbon permeation, first off, I'll say all pipe types are susceptible to this because the gaskets in all pipe materials for bell and spigot are susceptible to hydrocarbon permeation. There's a Water Research Foundation report actually put out, this is probably 8 years ago now, 7-8 years, and where they wanted to see, who's being affected by hydrocarbon permeation. And the study actually found no instances of polyethylene pipe, but found plenty, especially under, houses and driveways, personal driveways that found, hydrocarbon permeation through gasketed joints. Alan, yeah.
Yeah. So one of the things we do as competent, responsible environmental engineers when we can is if we know that there's hydrocarbons within that area or brownfields for other terms, we don't install pipelines there. We try to route around it or we clean up that hydrocarbons that are there and left through it. So that makes logical sense in that manner. But if you're not afforded the opportunity, high density polyethylene offers dual containment. So it's a pipe within a pipe, and those are used in landfill applications all over the place to get leachate, some really nasty stuff out of landfill. So HDPE is not unfamiliar with hydrocarbons, and we know how to handle it. So there you go.
Perfect. Thank you, Alan. Yeah. On top of that, there's also a polyamide, a nylon wrap, just like the ductile iron guys would wrap ductile iron pipe to keep water off of it, to keep corrosion away. If you are going through a hydrocarbon contaminated area, you can also wrap polyethylene pipe in a nylon wrap that is insusceptible to permeation. So again, if you can avoid it though, just avoid the brownfields, try and go around. Gaskets, other issues with gaskets, chloramines. Chlorine as well is rather aggressive towards rubber gaskets, but chloramine is by far the worst. We have a lot more cities across the country that are going to chloramines. Right now, we're about 10 to 12, maybe 13% of the market as a disinfectant for chloramine, but it is getting better and more commonly accepted. And so chloramines, while great for pipe materials, are very aggressive towards rubbers and gasket materials. So in those areas that are making the changes, there are chloramine resistant gaskets, and they move that direction as well.
One of the balancing acts that water operators and treatment plant operators have to go through is to look through those disinfection byproducts that could be as a result of disinfection bonding with organic materials. So that's why chloramines kind of came onto the scene. They're actually as old as traditional chlorine themselves or thereabouts, but there is definitely a balancing act of what happens in the pipe as we transmit that fluid through it and what happens within your pipe network. You got to watch it.
Absolutely. Continuing on with the gasket conversation, the EPA actually did a study, and this was back in 2015, so 7 years ago now, to find out how they were getting water contamination in bell and spigot jointed systems. And so they were finding that if you have a leak through a gasket, during normal situations, you would be exflowing, putting water out of that leak. But during a water hammer or a fatigue cycle, you would actually be pulling that now contaminated or potentially contaminated groundwater into the system through a low pressure spike on the other side of a cycle of a water hammer event. And so they actually have a whole a paper. Here's the link. Please copy paste and go read this study when you have time, but showing how, potentially, again, contaminated groundwater can come back into a bell and spigoted pipe system through contaminated groundwater. So HDPE pipe, again, completely thermally fused, leak-free from point A to point B, so we don't have to worry about any of that potential. For the longest time, we've been giving presentations about polyethylene pipe. We talked a little bit about PVC. We've really been talking about PVC for the last couple of years. But as a professional presenter, whatever I want to consider myself, you feel like sometimes you're just howling into the wind. And here a while back, the PVC industry came out with a press release coming out and saying, "Hey, polyethylene guys say we leak. We don't leak." And what they're referring to and what we're referring to is in their AWWA manual, during their pressure testing, they allow a certain amount of leakage, of gallons lost. And I think they're trying to change the terminology that they use in that, but it's still ultimately, water loss over time during a pressure test. And so they came out with this press release saying, "Hey, no, we don't leak. This is just the pipe relaxing, moving, coming into its final position during the pressure test." Ductile iron guys did the same thing. They didn't do a press release. They actually did a YouTube video. So the ductile iron industry came out with the same information. Neither of these guys changed their standards, though. And what it really came down to is polyethylene pipe. We have the same thing. Like, the pipe is going to move and kind of figure out its final resting place. It's going to expand a little bit with pressurization. And we've taken this into consideration. So when you pressure test a polyethylene pipe, you actually do a initial pressure up where you overpressure the pipe past its test pressure. And this is going to make sure that the pipe has fully expanded, it's moved, and it's got into its final resting place. And then you start your timer for your test. You bring it down to your test pressure and you start your timer. And when you pressure test polyethylene pipe, you are allowed zero. And I mean zero leakage, zero pressure drop. We're making sure that that is a leak-free system from point A to point B. PVC guys, the ductile iron guys, they can fix this exact same problem by establishing the same testing criteria where they do an overpressurization, a time where they have relaxation and the pipe can become uniform, and then start their timer. But they will not do that because we truly do believe that there is going to be that bell and spigot leakage from day one.
Okay, so you're saying that it does leak during the testing?
Yeah.
And that the standard permits that?
Correct. Yeah, and even if you want to say, like, well, if it's perfectly installed, it doesn't leak, great. That's great. But your standard still allows for a certain amount of gallons lost. And so that's what we're trying to get them to change. I
got a question that Matt just responded to, which I really think you need to answer. The question is, it was in regard to something you just said, Dusty. What about contraction and expansion due to temperature differences, which is the major reason not to use PE pipe, especially over long distances?
Love it. Love it. Love it. So the Bureau of Reclamation did a study here. This is about 3 years ago now, on soil friction, soil pressure, and expansion and contraction of polyethylene pipe. And so if you have a water source, let's say one water source is below ground for part of the year, one water source is above ground for part of the year, and the temperature differential between those two is, let's call it 30 degrees. And we have a mile of pipe. If that mile of pipe was above ground and you saw that 30-degree temperature change, that could be a lot of expansion or contraction in polyethylene. But the thing about polyethylene pipe is it has a low elastic modulus. And so even with it wanting to grow and shrink a lot, it doesn't have the strength to overcome soil pressures. So with proper burial, especially if you're using like sands and gravel, something that really bites on, that pipe's not going to move. Even with temperature extremes, that pipe is not going to be able to overtake soil constraint to be able to expand and contract with that temperature change.
Okay, but with a 30-degree delta above ground, which is something that Xylem and United Rentals deals with all the time, Dusty, on their temporary, how do they deal with it so that it isn't ending in somebody's living room?
Yeah, no, estimated deflection, we'll call it. So knowing exactly how much pipe is going to want to expand and contract, and making sure you're restraining that pipe at certain areas where you do not want it to expand and contract at. If you go out to the oil fields, it's very common to see polyethylene pipe like spaghetti noodles, just all over the ground. Everything's installed above ground, nothing is buried. And we had a 16-inch line up in Wyoming, up in Casper, Wyoming. They just put it along the side of the road in the winter, installed it, and came back that summer and somebody hit it with their truck because it expanded and it walked across the road. And so they came back in. Part of that line they wound up putting through the trees, but they put some concrete barricades out there as well, just to make sure that where it expanded, they were controlling. They weren't allowing that pipe to go out into the roadway.
Great. We're running a little behind, but I think these questions are awesome. We have about 3 open questions right now, so keep them coming. Thanks, Dusty.
Awesome. Thank you, Peter. So just kind of go back up a little bit. Let's talk a little bit more about PVC's history, so we can talk about, some of the potential issues that we really, as engineers, need to be designing to get away from and to stay away from potential issues. So 1986, PVC industry changed AWWA C905. They increased the pressure ratings, lowered safety factors, and there was no change in materials. It was just, hey, C905 is large sizes, which is predominantly transmission. And in transmission pipes, we don't really see a lot of cyclic fatigue. So therefore, C905, we're going to allow to have higher pressure ratings going from this day forward. And it went through, got blessed. And so overnight, a DR18 went from a pressure class of 150 to a pressure class of 235. So then in 2007, the PVC industry went back to AWWA to change C900. C900 is their smaller diameter distribution standard at the time. And they said, hey, we've had great success with C905. We haven't seen a lot of failures, but they've really just, didn't take into consideration that distribution systems see a lot of cycles. They see a lot of water hammer events. And they said, well, we didn't have failures in C905, so C900, let's just go consistent across the board. And so again, no change in materials, no cell class improvements, just overnight stroke of a pen, higher pressure classes in C900. And then final change in 2018, they took C900 and just made that the one standard. There's no longer a C905. It is now distribution and transmission all in one standard. This will probably happen for polyethylene pipe in the future as well, where C901 and C906 will become one standard. But again, that's just because there's so much consistency between the two at this point. So with that change, though, for the PVC industry, it put all of that design criteria for cyclic fatigue and fatigue failure onto the engineers. And it said, hey, if you're going to use PVC, we're going to rate it at this higher static pressure rating. But if you have flow velocities, X amount, this many cycles, this much fatigue, you need to be designing it for those cycles. And so overnight, they were able, again, to increase the pressure classes to better compete with ductile iron's 350 PSI pressure rating. But they kind of did it with a sleight of hand, putting all of the onus of design onto the engineers and taking it away from the standard. So HDPE pipe, we really didn't see, it's a monolithic pipe system, and those are fully restrained, self-restrained fusion joints. So one of the other system failures you find with PVC ductile iron is if you don't thrust block them correctly, you're going to have, gasketed fittings push off at the end of the pipe, whether it's a T or an elbow. So HDPE pipe, again, is fully self-restrained. You weld it together and it's not going to come apart. And there's no need for thrust blocking unless you're transitioning to another pipe material. Oh, and we have ASTM standards for everything when it comes to HDPE pipe. Again, people think we're the new kid on the block. We're not. We have ASTM standards, AWWA standards for everything. Speaking of M55 at AWWA, the HDPE pipe manual for design is brand new. Make sure to go out there and get you a new copy.
Dusty, we've had a lot of great questions here on length growth during pulling for trenchless applications. So if you are pulling that pipe into place through horizontal directional drill, yes, you're going to put it under some tensile force and you may have some elongation. In the good old construction terminology, what we want to do is measure twice and cut once. So that contractor himself will fuse on a longer length of pipe to make sure that when he pulls it, it's not going to be short. Then they allow it to relax. Then you make that terminal connection itself. So
that's great. And there's two ways that we're allowing this to relax, by the way. So when we do a directional drill or a pipe burst, however long it took to pull into place, we're wanting to make sure to allow it to rest that same amount of time for any strain that's left over in the pipe from that pull. But on top of that, we need to let that pipe temperature become the same temperature as the ground. In the wintertime, this isn't quite as important, but in the summertime, if we're July doing a directional drill or a pipe burst, and this pipe string has been sitting above ground, that pipe string could be 140 degrees. where your ground temperature is 60 degrees. So Alan hit it right on the head. When we do that pull, we're going to bring it through and we're going to keep a little bit long on both sides.
Surprisingly enough, that relaxation period is typically in the 2-hour range, but we allow, as conservative belt and suspenders engineers, a 24-hour time period thereabouts. So we're doing pretty good. We got about 30 minutes left, and we've had well over 20 questions. So keep them coming, and we're going to keep Dusty moving along. So that way we can try to get through all the material for everybody. Way to go.
Thank you, Alan. So going back to cyclic fatigue. So for PVC pipe, this is going to be ultimately, when the pipe was installed perfectly, no over insertion, no over deflection. This thing was put in, best contractor in the world, got the best contractor award that year, and this pipe is designed perfectly. The ultimate failure method of this pipe is going to be fatigue. It's going to be a cyclic fatigue failure. So for PVC pipe, you can handle about 100,000 cycles. For HDPE pipe, we have testing now that shows we can have over 10 million cycles. Cyclic fatigue is not a design criteria for polyethylene pipe. It's just not a means of failure for us. And so we actually had a University of Texas Arlington did a study on polyethylene pipe, DR17 rated 125 PSI, took it to 2 times pressure class, so 250 PSI over 10 million cycles. And then my favorite part that wasn't in that report, since we know Harvey Svetlik, Peter mentioned him before, he provided the pipe for this testing. He took some of that pipe sample off test and then tested it for new pipe criteria, tensile strength, elongation, all those things, and it still tested it as a brand new pipe. So again, cyclic fatigue for polyethylene pipe is not an issue. So the American Waterworks Association actually did a study a while back trying to find out what's the average amount of cycles per day that your typical water distribution system sees. And so if you take that 100,000 lifetime cycles allowed for 50 years, that's 5.5 pressure cycles per day is allowed. And that's a 50-year life. The amount of cycles that you have in a typical distribution system are actually much greater than 5.5 per day. Oh, right. That was the bird. I was like, what is that noise? So
we put that video in for you, Dusty. And while it's not the constant pressure surge that they test at the facility for the resin, when basically they have lots and lots and lots of these pipe samples in different controlled temperature areas, as to which they're constantly running that occasional and recurring surge through it to be able to prove the hydrostatic design basis that makes up the pressure rating of this pipe. This test is a quick burst test to show you just basically at the extrusion facility what it could be like as it fails. So this pipe, if it's a DR11, from what I've seen, could be failing at 1600 plus PSI through that quick burst test. But I unfortunately, we didn't have any footage of the controlled chambers thereabouts, but maybe Dusty, if you want to elaborate on the testing, that would prove some of this cyclic pressure resistance that's really backs up that claim that we've solved for fatigue.
So HDPE pipe with that low elastic modulus, the entire piping system acts like a giant shock absorber. And so where you have, let's call it 5 feet per second flow velocity through a pipeline, if that's in polyethylene and you have that flow stop, you're only going to see maybe 40, 50 PSI of a pressure spike, where in PVC, you're going to see a couple hundred, and where in ductile iron, you're going to see 300 to 400. It's going to be a very violent, a large pressure change. But again, HDPE pipe, if you look at how this pipe is failing, it actually stretches to the point where it has thinned the wall and finally allows it to fail. Look at the expansion before the failure. The other thing I like to point out here is that failure is localized. We maybe lose a foot of pipe that has to be replaced, and you move on. The other thing I will mention is you are rarely going to see that scenario in the field. Alan hit it right on the head. We're talking 4 to 5 times the pressure rating of the pipe to actually blow it up. So the only time you run into that is if somebody's doing a pressure test on it and their gauge is broken or not calibrated, and they just keep putting more and more pressure, and it finally yields the pipe. So very, very rare that you'll ever see that type of failure in the field. So PVC's favorite argument is, hey, if you use polyethylene pipe against PVC, you need to have 2 things. You need to have the same inside diameter. You need to have the same pressure class. And so what that forces us to do is if they go out and say, hey, we've got a DR18 here, rated at 235 PSI against static pressure rating, you have to use a DR9 polyethylene with 250 PSI pressure rating. And that forces us to go up another diameter to get the same inside diameter as the PVC original design. And this is absolutely not the case. The first question out of my mouth is, what's your service pressure or your working pressure of that application? And usually it comes back, 80 PSI, 100 PSI, something like that. Where in that case, you need to be going DR for DR with PVC pipe. Because again, that 235 PSI, while it is a pressure rating, it's not a flow velocity pressure rating. It's a static pressure rating. So the math really comes down to it. Anytime you're running at 5.5 feet per second or more flow velocity, you should be quoting DR for DR, polyethylene versus PVC. So if you have an 8-inch dips DR18 PVC, you should be quoting against a DR17 polyethylene system. And then I love putting memes in these things. They feel rather dated. I really need to stay on top of these things. This was a funny meme 2 or 3 years ago, but now I got to come up with something new because memes move fast and I got to stay on top of these things. There's also a great calculator out there for anybody who wants to use it. This is free to use. It is called PPI Pace at ppipace.com. This allows you to do exact side-by-side comparisons of ductile iron, PVC, and polyethylene to see how they'll react in your systems. So here we have a 10-inch dips, ductile iron rated at 350 PSI, DR17 poly, and DR18 PVC. Side-by-side comparison, working pressure 70 PSI, temperature 57 degrees, and then we're looking for a 100-year minimum design life. And so it'll actually come through here and it'll give you, hey, what does this look like? Sorry, I also want to mention design velocity here is 4 feet per second, and occasional velocity, so fire situations, things like that, is 8 feet per second. So still pretty conservative. And here we can see PVC failed and ductile iron failed. The reason ductile iron failed is because a flow velocity of 8 feet per second in ductile iron, because of its high elastic modulus, is going to create an extreme pressure cycle. So you actually get 100 PSI above pressure class for ductile iron for a surge. And this far exceeds it. I think we're sitting at 590 PSI total on ductile iron. PVC was totally fine as far as the surge pressures, but the amount of surges, your design life is going to be about 24 years before you hit that 100,000 cycle life. This is actually a recent, I literally do these all day. People call me every day. Hey, I've got this PVC job. We want to use polyethylene. Customer wants to use polyethylene. What size should we use? And so I'll go in, we'll run the math. And so they came through and said, hey, we want, to upsize. I'm like, you probably don't need to upsize, because they wanted to put in, a very, very thick DR11 for this application. And so we did a side-by-side again comparison. DR17 is rated at 125 PSI, and that is at 5 feet per second. They had a very, very high flow rate on this. And I think they were using a DR25 PVC. And come to find out, we can go with a very thin DR21 polyethylene and keep those same inside diameters pretty close. And they were able to use polyethylene without having to do that upsize. So continuing on that pipe comparison, PVC pipe, again, very, very strong, has a higher tensile strength than polyethylene pipe, but it's not really needed. You really don't need these high tensile strengths for most of the applications. Really, it's designed beyond the point of need. One other thing I love to point out, here, talking about all of our AWWA standards earlier, is, this is a warning that's in the PVC manual. And I don't know who else on here enjoys watching TikToks. I love it, but not for the normal reason most people probably love it, watching dances or whatever people watch. I love to watch it because every contractor has some 20-year-old kid or 25-year-old guy working on their crew, and they video everything. They video all day long, almost, it seems like, and they just put this stuff up for free. So me as a pipe manufacturer, I love to go out there and ask my customers, like, hey, can you get us some pictures or some videos? And I never get anything. Nobody ever responds to me. And then I just go on TikTok and I'll type in HDPE pipe or directional drill or whatever. And there's some 25-year-old guy on there on the job site that has videoed their day and put it up for free. And this is one of those. This is Dante Dante's tapping some PVC. There are so many things wrong with this. Absolutely, like if the PVC industry saw this, you point out at least half a dozen I can see. They can probably see more than that of things that were done incorrectly here. First, he is tapping directly on top of that pipe. You should never do that. He's using a drill. You can hear the drill bog down. Again, he did everything wrong. But again, with polyethylene pipe, HDPE pipe doesn't fracture. During taps, during bending, whatever the case, you're not going to have blowouts like this.
Could
Now,
be easily observed that the trench wasn't exactly a safe condition, as
No.
well as it was above his shoulder, which is that OSHA established height. But we do
Yes.
learn more from failure than we do from success. So in this instance, we are going to learn from Dante's failure and never forget some of that as we go through. So
That's
Dusty,
right.
definitely thank you for sharing.
Thanks. Again, now we're getting into fusion. So, what's the real benefit here of polyethylene pipe? Sure, it's very flexible. It's very ductile. It moves with ground movement, whether that's freeze thaw, seismic events, drought events. You're going to move with the ground. But what it really comes down to, the biggest benefit of using polyethylene pipe is fusion. If you don't believe in fusion, if you don't believe in the fusion strength of being as strong as the pipe itself, you're not really seeing what polyethylene is for its full system. You're not taking advantage of everything. I literally just got off the phone this last week with a customer doing a 30-inch dips project using ductile iron fittings to connect every 50 feet of polyethylene, and he's having failures. And I'm sitting here like, why did you not rent a fusion machine and butt weld this? He's like, I like to bolt stuff together. We just prefer bolts, and just completely floored me. So now they are fusing. They tried one fitting and it didn't work so good. And again, these were non-polyethylene pipe fittings. They were only for ductile iron pipe, and they didn't work on polyethylene. He just couldn't believe it. And so they're now redoing that all with fusion. We have all the testing and all the fusion standards. So F2620 is the fusion standard. It also includes a test method in there. It's called reverse bend or bent strap, what you can do on pipe walls of 1 inch and thinner. You have D638, which is in lab tensile testing, tensile impact, high-speed tensile impact. You have a lot of standards out there to test the fusion strength of polyethylene. And again, their claim to fame is the fusion joint is as strong as the pipe itself. Stephen, you had a question?
Yeah, Dustin, I just wanted to, we had a question in the Q&A section on, talking about the differences between HDPE and they said specifically fused PVC. And, that has a broad range of answers, but while you're showing this information, I think it's very important to note that a heat fusion weld by polyethylene and one by PVC results in a very different joint. They may look the same, they may use similar equipment, but molecularly, the polymers don't join the same way. That's why you said that a joint of polyethylene, but fused the right way, gives you a joint as strong as the pipe. In a PVC butt fusion failure, it's not as strong as a pipe, and there's very specific reasons for that. So everybody needs to be careful with that. Make sure you look into it and do your due diligence to make sure you're getting what you think you're getting.
Yep, that is exactly correct. And I'm sitting here trying to find on my desk my fused PVC sample. I have hundreds of these things to kind of demonstrate what the difference of the way it looks. But Stephen hit it right on the head. With a fusion for polyethylene, you have a full molecular entanglement that is going on, that is providing not only the tensile strength, the same as the pipe, but also the ductility and bending of the pipe itself. And we'll really drive that point home here in a few slides when we talk about swage lining and tight fit liners. But again, the tensile strength of a fusible PVC is not that of the pipe strength versus a polyethylene, which is. RCP, we can talk about RCP. This applies to every pipe material. Every pipe material can have RCP, which is rapid crack propagation. But you have to have exactly the right criteria going on in your system to be susceptible to rapid crack propagation. This is something that we understand all the way through with polyethylene pipe because we are used in natural gas distribution systems. You have to have in compressed air systems great RCP resistance to make sure that you're not going to have some kind of a long running crack if you are struck by a third party backhoe, bucket, whatnot. So this is something we absolutely understand with polyethylene pipe. So different ISO test methods to do this. And what we found is that RCP can occur with just 2% entrained air in PVC. HDPE pipe, it takes a minimum, where do I have it for polyethylene? It's like 15%, I believe. I'm so sorry, you guys. I thought I had this in my previous order. Oh, dang. Sorry about that. So again, it takes much higher. It might even be 25% entrained air. Oh, right there. Sorry. 25% entrained air for RCP to occur in polyethylene pipe. The other side of that as well is that the amount of stress put on the pipe by pressure inside of it is only 10% of the pressure class for PVC, and you are susceptible to RCP, where you have to actually be operating outside the pressure class of polyethylene to be susceptible to RCP failure. So again, RCP is not really an issue for polyethylene pipe, and the best way to present RCP is just use HDPE pipe, because again, there's no criteria that you're running inside of our prescribed pressure ratings that you would be susceptible to RCP failures in a water system. Alan.
So Dusty, I love it when sometimes you could just see when the light goes off and, bing, ding, 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 there it goes on. It's just great when you share that with us as well. We've gotten some questions that said, or comments more so that, you know what, if that pipe can be used in the natural gas market where leakage means people blow up and houses blow up, then it darn well better be used with potable water. And you got it. That's it. Exactly. So
exactly. And I love that light bulb going off here in the West where I live, because we don't have water right now. That is number one headline news anytime it's talked about is water. And so any drop of water that we can save from point A to point B by getting rid of leakage in a piping system, we're ahead of the game. That's absolutely the best thing that we can do. We've been to plenty of cities across the US that have very high water leakage rates, and they don't care. Niagara Falls, for example, very high leakage rate. They don't care. They have plenty of water.
On the next slide we've got coming up, Dusty, we've got a great cameo by a well-respected, oh, hey, look, it's Dusty. There it is. I'm not sure if the sound's going to work or not, but if it doesn't, Dusty, please make sure that you narrate it for us. I think I was taking the video at this particular moment too, and we were in the lovely city of Napa on a pipe bursting project. And here you go. Without further ado, let's see the cameo from the man himself.
As I say, there's nothing more cringe than having a video of yourself in your own presentation. So I'm not going to play it. I'm actually just going to voice over this thing. And all we're talking about here is productivity. We have one gentleman working the fusion machine behind me. He is doing 6-inch pipe for a pipe bursting string, 500 feet at a time. And he is welding that, taking it out of the machine, moving it down the line, welding another joint all by himself. This is a one-man show. And it's just an extreme way to show how productivity works with using polyethylene pipe. This is then drug to the insertion pit and where the pipe bursting begins.
Just for the record, Dusty didn't put the video in. I did. So there you have it.
Thank you for taking that.
I think
it makes me not look so.
Put a video of himself in, but not Dusty.
I would, yeah, exactly. Moving on to the ductility of things. So I spoke at a SPE, a plastic engineering conference a couple of years back, and really wanted to highlight the ductility and the flexibility of polyethylene compared to other plastic pipe materials. So here's a few slides from that. On the left here, this is a dock in Hawaii where the end of the dock is on the right side of the picture. It just ends, and they couldn't float it out into the taxiway because of boat traffic. And so they actually hired a crane as they were fusing the pipe, and they would just take it straight up into the air as they fuse on it joint after joint. The picture there on the right is a pipe string in Florida, several hundred feet put together. This was also large diameter, getting ready to be pulled in to a directional drill. Here's another directional drill, 20-inch installed under I-5 in California. And then we have dual 42-inch there in Utah, Salt Lake City, where I'm at. And again, the big thing I like to show with this is with polyethylene pipe, it is so ductile and so friendly to use and install that you're not having to use a ton of equipment to make sure that you're keeping your bend stresses down, because if you have a bend stress on other fusible plastics, you can absolutely snap a fusion in half or break a pipe. And so with polyethylene pipe, you're using very little equipment to handle this stuff, where other fused products, you are using quite a bit of equipment to make sure that you're not putting any undue stresses on this pipe to prevent any failures or overstresses. Pipe bursting, this is absolutely where polyethylene starts to shine, is in trenchless applications. We are by far the predominant material when it comes to trenchless installations. And the biggest reason for is because of our flexibility, because of our ductility. The insertion pits and the exit pits are the smallest of any pipe material, again, due to that flexibility. And there's lots of different options when it comes to trenchless. Static pipe bursting, pneumatic pipe bursting. And I will also mention that polyethylene pipe is the only allowed pipe material in pneumatic pipe bursting for sewers, because that is such a violent process using a hammer, a pneumatic hammer at the beginning of the line, that there's no other pipe material that can hold up to that cyclic stress of that pipe bursting from pneumatic pipe bursting. So it's just polyethylene. One of my favorite case studies, we're going to go through a few here now. I'm glad this is finally out of litigation with the city of Seattle, so we can talk about it. This is King County, Washington, where they did attempt one was a 34-inch fused PVC pipeline. This is a directional drill. Both polyethylene and fusible were optioned for this job. Both would have absolutely worked. The contractor, for some reason, went with fusible PVC the first time, and this was for a drainage system down to, it was very, very deep directional drill, by the way, and it was down a hill, and it would collect water into a tank anytime it rained, so that you could treat that water before they released it into the Puget Sound. And the first rainstorm came after the installation, and those tanks did not fill. There was no water. And so because there was no water, they camera inspected the line, and they found that there was catastrophic failure, and the line was completely full of debris. They went back through and said, well, attempt one didn't work. Attempt number two, let's actually try and use that pipe, and let's pipe burst it. Let's use polyethylene pipe now and pipe burst brand new DR14 PVC and pull in polyethylene inside of it. And it worked. They absolutely did it. This was 2 times the stresses of the original application, the original installation, and polyethylene still was able to do it. So again, polyethylene pipe, perfect for trenchless applications. Here's the compressive fit, what we call swage lining, where we're going to take a slip line, but we want to maximize the inside diameter of that slip line. It's easy to pull in a smaller slip line and grab the annular space. In this case, we don't want to do that. We want every millimeter of that inside diameter for flow. And so we're going to take a pipe size of polyethylene that's larger than the inside diameter of the hose pipe. We're going to take it through either a set of box rollers or a swaging tool, which is just a die. That's what you see here. And it's going to reduce the diameter of the pipe down to, let's call it 2 inches smaller than the hose pipe. And while we do that, we hold a tension on the pipe that doesn't allow it to go back to its original diameter. And by doing that, we now have a smaller diameter that we can slip down the pipe, the hose pipe. And by the time it gets to the other end, we now release it, release the tension on it, and it'll go back to its original diameter, or attempt to, and become a snug, tight-fitting liner against the hose pipe. And so this is the biggest thing for me to show the ductility and the strength of a fusion. Sure, this is impressive for a pipe to go through. Of course, it's impressive. But it's even more impressive when you realize that there's a fusion every 40 feet on this line, every 50 feet on this line. And it's going through that same amount of strain to reduce down to the smaller diameter. Incredible amount of stress of ductility in polyethylene pipe. Plow installations, they're on the left. We have 24-inch diameter going 6 feet down into the ground. I don't want to break the illusion here, but it's not just that machine. You also have 2 plow winching machines up ahead of this to help you, to help pull it and create the plow in the ground. It's not just this machine here with these little tiny tires able to plow for 24-inch pipe in the ground. There's also 2 support vehicles out ahead of it, winching machines, to pull that pipe, that plow along. But this is very, very common. You go anywhere now, you see a dozer hooked up with a plow, and they're putting conduit in the ground. This is very, very common now. Field performance. So even though we did talk about a little bit about this before, we did solve for that original, corrosion issue with plastics, but with PVC, we did again introduce something new. But we'll talk about polyethylene failures in the future as well. And so I get these questions all the time, like why, or really put the comparison out there. what is the comparison of ductile iron, PVC, polyethylene pipe? And so again, I like to go to the memes. I put this meme together myself. I'm like, okay, ductile iron, their claim to fame is strength. We are the strongest pipe material out there. We have the highest tensile strength, highest elastic modulus, the highest everything. We're the strongest one out there. And there's a podcaster I listen to who he has a friend who's a bodybuilder, and he calls him big for nothing because he doesn't have a job where he uses his strength. He doesn't have any hobbies, that require this great amount of strength. He bodybuilds. He gets big and strong for the sake of being big and strong. And so for ductile iron, that's the guy on the left. Absolutely. What's this strength for? Big for nothing. It's just strength for the sake of strength. In a normal application, that ductile iron pipe is never going to need to use that strength that they have and claim to be the best for. And so moving on, I'm like, okay, so who's the net? What is PVC? If we're going to keep this weightlifting thing going on, what is PVC? And PVC is the guy that skips leg day. That is absolutely PVC. Hey, we have a higher tensile strength. We are the strongest technically plastic in the industry, which is absolutely true. Tensile strength, 7,000 PSI. Instantaneous elastic modulus, 400,000 PSI. It's a very strong plastic material that is absolutely susceptible to fatigue failures. So great upper body strength, absolutely is skipping leg day. And then what's HDPE pipe? And I really thought about this for a long time. There's a lot of athletes that I could have considered, but I'm like, you know what? HDPE pipe, that's a gymnast. That's someone that is very flexible, very strong, is perfectly suited for their application. Exactly the muscle strength that they need for whatever their routine is, they do. And so HDPE pipe, we are the Olympic gymnasts of the pipe world. And so this was a fun little meme that I put together just this last year to really drive it home for customers that want to know what is the difference. And so the cost technology, again, failure cost, this shows the polyethylene pipe, again, very, very few failures for polyethylene. Not a lot of pipe in their system, though, at that time. More and more polyethylene is going to the ground in Calgary today, though. So cost comparison, this is pre-COVID. I'm not even going to go over this anymore because it's completely out the window. Lead times and cost, that's the whole reason everybody's on this call today, just because they're all over the place. It depends on where you are in the country. They are literally all over the place. So let's talk end of life scenarios. So for polyethylene pipe, we very much understand what our end of life looks like. For ductile iron, it's corrosion. For us, it's pinhole leaks. We have so we talked about quick burst, overpressurization, the tearing apart of the crystal structure of a polyethylene pipe. The other failure method, which will be the ultimate failure method of polyethylene pipe, is what's called slow crack growth resistance. And slow crack growth is understood by using a test called the Pennsylvania Notch test called PENT. And for the original 4710s over 10 years ago, it was required to have 500 hours of PENT, slow crack growth resistance. And that would equate us to 100 years in the ground service life, resisting, again, slow crack growth. And the materials we're using today, PE 4710s, are well over 10,000 hours. So, a 20 times multiplier on, this 100-year service life, minimum 500-hour PENT test. And so we understand the failure method still of polyethylene pipe. We just don't know how long that is. We know for a fact that it's well past 100 years, but the service life is really getting out there now. But what I want to really talk about that nobody else is talking about, and I mean, I go to all the conferences, I go everywhere, no one is talking about this. We are very familiar with how to fix broken pipe systems, okay? Peter Dyke, again with the Alliance, has put together a spreadsheet of most of the major municipalities in the country and their pipe system replacement, how often and how fast they're replacing their pipes. And if every one of us out there, ductile iron, PVC, polyethylene, claim a 100-year design life, we need to be replacing an entire city's piping system every 100 years. And many of these cities, hundreds of them, are well over 400 or 500-year replacement cycles for these pipe systems. And so where this is going to become very dangerous in the future is in all these pipe systems that are PVC, we don't have the typical failure that we're all used to. If we have a corroded or a circular fracture or a corroded ductile iron, we dig down, we put on a band clamp, and we're back up and running. And it's a good Band-Aid for quite a while. Or maybe you're replacing a small spool piece with 2 band clamps or a mechanical joint of some kind. We understand this, we know this. It's rather inexpensive to fix pipe doing this. PVC, even if it lasts its whole 100 years, it gets all the way to 101 years and it starts coming undone, it's going to start coming undone faster than we're replacing the pipe today. And so when we start having these failures, these fatigue failures, which is the ultimate end of life for PVC, no one is talking about this right now. If you're not replacing it fast enough and it gets to its end of life, these are catastrophic failures of your entire systems. So again, nobody's talking about this. This is axial fractures, taking out lengths of pipe. Alan, yes.
So we are right up at that time, and I think we've only got 1 or 2 slides left.
Literally one.
There you go. So for those of you on the call that want PDHs, we do a survey at the end of the webinar. And if you want to tell Dusty he's crazy, he needs to show you his legs to see if he skipped leg day or not. That's the time to put in that survey result as we go through there. But if you want PDHs, it makes our life a little easier if you put it in the survey. So please make sure you do. And he's going to finish up. We're here to help. And I'm so glad everybody's here. Dusty, definitely great job. Keep going.
Hey, thank you very much, Alan. Yep, and we're right at the time. So this is literally my last slide. I thank again everybody for coming today. You know, we have hundreds of people on the call today. And again, thank you so much. If you guys need any of our help, next slide, I actually have all of our contacts. Please reach out to us. That's literally our jobs. We're here to support people in this transition and education to more polyethylene pipe.
Yeah, great job, Dusty. You're right. It really is a transition. It's a transition from using materials you're comfortable with to a product that's a little different. It's got different characteristics, but does provide better service. So good job. Please answer the survey and say, yeah, I want PDHs, so I can prove to my boss that I did indeed sit through the full 75 minutes. Great job. Come back and see us in another month in mid-September when you'll hear our Alan Ambler talking about pipe bursting. So let's hear it for Dusty Langston. All right, if everybody could talk, we'd hear it. And thank you to the bench. You guys answered 58 questions. Congratulations. Great job. And stay tuned, answer the survey, then sign off. We'll keep it going here for a couple more minutes. Thank you all very much.
Thanks very much, everybody. Have a good day.
Bye, everybody.